Dr. Nuriel Amir. I worked for a company called Micron, and previously worked for a company named Mnemonics, and previously 11 years for Intel. Now all of that in the same office. The company just changed names. It was originally a fabrication facility called Fab 18, made by Intel in Kiryat Gat in Israel. So my current role there is the manager of the R&D, research and development. I was asked by Professor Shachar to present here a more practical point of view for this course. I will focus on the practical things, not so much on formulas, not so much on actual calculations. What I want you to get out of this class with is the feeling, the intuition of what to do and how to do, why are things done. So let's start with why are things done in this industry? Why are we doing things one way or the other? What is the motivation? Anyone? Cost. Very good. So we do all of this to optimize on cost. The reason for optimization on cost is that once you can do something cheaper, you can do more of it, and it can penetrate everywhere in the market. For example, I guess each one has a cell phone, right? This was not possible unless the microelectronic revolution. These key computers, all of this is thanks to the microelectronics revolution. Yes, slide demonstration, thank you. So, cost is the thing we optimize on. Not necessarily do it in the best way, in the perfect way. Once we know that, it would be easier to understand the motivation of many, many other things. So, let's start. The topic today is semiconductor fabrication. And I will talk specifically on the process flow. I will define what is a process flow in the next few slides. But let's start with what is the fabrication of semiconductors all about. So we start with a long set of activity on a wafer of silicon. Next class I will bring a wafer to show you. Here I will have a picture. So what are the set of operations? You learned in the previous classes a set of operations. So you've learned about the implant, etch, litho, right? And those are the kind of operations we use to implement the process flow. Eventually, all of this is done to create what? Chips. What are in the chips? We create transistors, we create resistors, we create capacitors, we create interconnects that connect with them, and eventually this builds up into a chip. The chip can be a memory chip, a CPU, or any other kind of chip. We have very specific tool sets. We need specific engineers and technicians and a clean room area, all of this in order to fabricate the chips. The silicon is rotating between one station, for example etch, to another station, clean, another station, litho, another station implant, and many times it goes back and forth. Typically we have around 30 steps of lithography. So after every lithography, there's usually an etch process or an implant process, sometimes both. And then there's a clean process for removing the resist. So think about this kind of rotation about 30 times. This is the way the wafer rotates between the different stations. Now, obviously, the order needs to be very precise. If it goes to implant instead of etch, we call it a mist process. We have to throw everything away. So we start with bare silicon, or sometimes bare silicon with an epi layer. Have you learned about the epi layer? So it's on top of the wafer, there's a very thin layer which has better electrical characteristics. For example, it's cleaner. It has a lower dopant concentration. That is the layer in which everything is built upon. Yes. We call it epi for short. It's a word that comes from Greek, on top of. Okay, so the wafers rotate between all the stations. When they finish, about 2 months later, we have a wafer full of dye. What is the production floor? What we call the clean room. So it's an area where all the tools, all the machines are, where we call it a clean room because it's very clean. It's many, many times cleaner than an operating room in a hospital. It's at least 10,000 times cleaner. How can we say that? How do we measure the cleanliness? We measure it by the number of particles per cubic feet. So a hospital or an operation room is plus 10,000. It means that every cubic feet has 10,000 particles above the size of 0.3 micron. A clean room has only one particle of that same volume. We get that by a flow of clean air, filtered air that comes from the ceiling, takes all the particles down, and then all the time, even if we or the tools produce particles, everything is washed down. Okay. Why do we care so much about particles? What would happen if there would be too many particles in the air? Defects. So a particle which is of the size or of the same order of magnitude of the lines we make on the wafer will eventually result either in a short, in an open, or the worst case is something which is moving from being a short to being an open depending on temperature or other things. This will eventually fail in the field. So you buy a cell phone, it works. After a month or so, it stops working. So this is the worst a particle can produce, a reliability problem. So this is a typical silicon wafer with many, many chips. This is a 6-inch wafer. I can say that by by the area here. Can you see this flat area? We call it flat. For 6-inch wafers, it cuts part of the wafer. For 8-inch wafers, there's just a tiny sign which we call a notch. This is how we separate between the wafers. Why is it needed?
Crystal orientation.
Exactly. It helps us understand what is the crystal orientation. So I see you've learned about that. So every time this part is below, we know which crystal orientations are at the sides. For most fabrication operations, for most process steps, it doesn't matter. But it does matter for example, etches which are selective, which depend on the crystal orientation. This is an example of a final product. This is an example of a Pentium 3 produced by Intel. This is one chip out of many, many chips in the wafer. A wafer of 8-inch produced several hundreds of those chips that went into, I guess, your computers or at least your parents' computers. Okay, so now I will go shortly about what we call the words. The different process steps are like different words. And we will use those words to create a story. Now, it depends what order you use the words, what order you use the process steps. We can make a capacitor, we can make a resistor, and now the story I want to tell is a transistor. Okay, so think of this as a story. Now, before I continue, I want to tell you about a question I got after I finished this section. I said, and now we finished the transistor. And then someone asked me, well, do you repeat this 1,000 times to get 1,000 transistors? And the answer is obviously no. I will show how to make one transistor, but we do all of them in parallel. Okay? So I'll show one, but you can assume that there are 1 million or 1 billion transistors in parallel. For example, in the memory from which I'm projecting this presentation, there are 16 gigabytes. So typically 16 gigabytes, that's 16 times 8, right? Transistors. Now it's not completely true, it's just half of that because every transistor contains 2 bits. But that is the size of a typical chip today. So billions and billions, tens of billions of transistors in every chip. I will show just one, the rest are done in parallel. Okay. So this is a picture of the clean room. We can see how people are dressed inside. They're dressed in white, not because it's beautiful, but just in order to make sure that one can detect if there's a stain, if there's a crack, if there's a tear. And then you can see there are protective glasses and also a shield. The shield protects not ourselves, but it protects the wafers. So if we're breathing or talking, particles from our mouth get into the shield and not into the wafer. And then you can see this tube, it pulls air out of the helmet, out of the shield, so the air comes in and it doesn't come out with particles. Okay. So there are many classes of fabs. Some use one design or another design. Some are cleaner and some are not. This is the cleanest standard that exists today for people. Here we can see a wet station. In order to produce less particles, there's a robot that takes wafers, puts them into bath. It's not only cleaner, but much more accurate. And here we see people doing maintenance on the tools. This is a less clean area. This is the backside of these walls, where we do maintenance. So this is a very short and schematic view of the clean room. Now I want to go over the order of the processing, but first a very short reminder of the different steps we will use. I guess almost all of them you've learned and you've gone through. So, and if not, and you have questions, please ask me. So the first one is CVD, chemical vapor deposition. In this process, we deposit either from heated gas or through plasma, which is called plasma-assisted CVD. We deposit material on the wafer. Those materials can be conductors, they could be semiconductors, and they could be insulators. So PVD is physical vapor deposition. In this way, we deposit by plasma physically atoms onto the wafer, and one of the ways this is done is by producing electrical voltage, cooling atoms, usually ionized atoms. That's how they are being cooled. Sometimes argon atoms, which are very big. They hit the target, and from the target we get spattered material out. This material falls onto the wafer and produces a film, usually used for conductors, metals, that can be used for other materials as well. Then, a third way of making the film is a diffusion area. We call it diffusion because originally those same tools, those furnaces were used for diffusion, for annealing, and also for introduction of dopants through diffusion. But nowadays, in the same tools, the main thing which is done is oxidation. So we introduce oxide atoms or oxide molecules, or we introduce water molecules. At a very high temperature, they react with silicon, and what we get from oxide and silicon? Glass. So we get glass, or we call it an oxide for the semiconductor business, very, very good insulating material. So what I want to mention is that we use oxidation also as a sacrificial layer. Sacrificial layer is a layer that is being later removed. To sacrifice it. We don't use it. One of the reasons is that the oxide doesn't only grow above, like a CVD or a PVD, but it also grows within. And for practical use, this means that the interface, if there are any contaminants on it, like metal atoms or sodium or anything else, eventually resides in the oxide. So when we grow an oxide, we take the other interface and we block it inside the oxide. And then we can remove the oxide. We have a very, very clean interface. The semiconductor oxide interface with silicon is one of the cleanest, most controlled interface we have in the industry. Okay? Lithography. So you've learned about lithography. I just want to remind you, we take a wafer, either with a layer or without a layer. We spin resist on it. Okay? The resist is being dropped, the wafer is rotating, and the spin covers the whole wafer. What we get later is we do selective exposure through a mask. So I don't show the mask here, but this area and this area got light. Intuitively, what the light does is break the connections. There are positive resist and negative resist, and I don't want to go into all of that. But in this case, where the line hits, eventually it gets dissolved and washed away. That is what we call developed, a very similar process to developing the picture. Now all the pictures are digital, but as a kid I developed with my father black and white pictures, so this is the point where we put the chemical which dissolves part of the paper itself. And then we're left with areas which are selectively blocked by photoresist. And this helps us define selective areas where we want to later do operations. Usually we do two operations after lithography. One operation type is implant, where we implant and the resist here blocks some of the implants, or hopefully all of the implants, and this area below will not get implanted. The other operation we do very often is etch. So the resist here protects the silicon below, or whatever we have below, and it won't be etched. Okay? So this is lithography. Is there any question? now an example of a wet etch. So now we can see we protected either with resist or with a different blocking layer. We protect this blue layer, and this layer is the layer we intend to etch. What we do, we put it in some wet chemical, okay, liquid chemical, we call it wet etch, and the chemical itself is selective. It does not attack the blocking layer or attacks it at a very, very low etch rate, and it attacks pretty well at a very high etch rate the layer we want to etch. Now, two things about wet etch. First, the advantage of wet etch is that we can choose the chemicals and the temperature very well, and we can get very selective etch. It means that it can etch one material with a very high etch rate and different materials with very, very low etch rate, sometimes practically zero. The second quality of wet etch is that it's isotropic mostly. Okay, there are some wet etch which are not. Isotropic means it etches at the same etch rate to all directions. Yes. Well, it is an advantage if you use it properly. So, one of the problems with the wet etch is that if the film is thick, it etches even beneath the protective layer. Why is that a problem? Why don't we want to? We can take this into account and we can allocate another half a micron for the etch beneath the resist. Changes the resolution, yes. The minimal line we can make, and actually, if we need to allocate some more silicon for that property, this is silicon we lost. This is silicon that will not be used later for anything useful, right? And why do we want to save silicon? Cost. Again, we get back to the motivation. If we allocate some silicon for that, it means that instead of producing, say, 200 chips from a wafer, we will produce 190. And those 5% which are lost are gone forever. 5% is a lot of money in this industry. Okay, so this is something we want to try to avoid, and I will show how we get rid of it in dry etch. Now, how do we stop the wet etch? What? So there are two ways of stopping the etch, determining how much we etch. So one thing is with time. If we know the etch rate and we know how much we want to etch, we calculate what is the relevant time and we stop it. So we take the wafer out of the wet bath, we call it, and we can do it after a minute. Say in a minute it etches 1 micron, in 2 minutes it etches 2 microns. So if we want to etch half a micron, we just put it half a minute. That's one way to determine. What's the problem with this kind of control? We need to calibrate the process all the time. Why do we need to calibrate the process? The etching material changes. Sometimes the bath itself with the etching material, when it's fresh, it has one chemical composition, and over time, the chemical composition changes, it dilutes, and so on. So the etch rate changes over time, changes from tool to tool, and we have a lot of variation. If we just control the etch depth by time, then we will get quite a lot of variation. So what is the other way of controlling the etch? What? Measuring in situ, actually,
allows you to better control the time. Better control also allows you to better control the time. But the quality of the wet etch that allows it to be selective is the key. Because if, for example, here, the wet chemical can etch this layer that we want to etch, but does not etch the silicon, then we know that in 1 minute it should etch all of it. We etch it for 1 minute, and then we do another, say, 10 seconds. We call it over etch. And it cleans whatever is left, but it doesn't touch the silicon because it's selective. Now, the film itself is not always the same thickness. Why isn't the film not the same thickness? What sources of variation could be there? How do we make the film? CVD or oxidation or PVD. Now, those tools also have variations. They don't produce every day the same thickness. Even if they produce the same thickness, it's not the same on the center of the wafer and on the edge of the wafer. There's some variation. Not every tool has the same variation. Some tools have it more uniform, some tools have it less uniform. Now, if we use a selective etch to do the etching, even if the layer in the center is thinner and it finishes the layer very quickly, we give it some time to over etch, then it finishes the layer at the edge of the wafer, but still it doesn't hurt the center of the wafer because the etching material is selective. So the selectivity allows us to overcome variations. Now, as opposed to most of the material you learn in the university, in real life, it's not the actual number you need to hit. It's the variation you need to control. It's very easy to say, oh, I have a 100 nanometer layer. I will etch it 1 minute. The key is not to determine how long to etch it, but to think about how to control the variation. Because in real life, there's variation in everything. And in industry, that's the key. Question?
But if you over etch it quickly, it changes the amount of etching to the sides?
Yes.
This depends also on those factors.
Yes, so if instead of 1 minute, you put it several hours, eventually this will go down, etch all of this, and this resist will lift off. And I've seen this happening. Yes, you need to control it also with time. You need to have some over etch, but not infinite time. Okay. Yes?
If we have a layer and I want to etch this half of it.
Yes. So you need to control it with time. Yes. Now, an improvement to the wet etch is dry etch. The reason we call it dry is because it's not using a liquid. It's done in an environment of gas, mostly an environment of plasma. So what is the plasma doing? The plasma has two properties. One, it physically knocks the atoms and sputters them out. Okay, like physical bombardment. The other thing is the plasma is composed of chemical materials. Those materials, if selected correctly, are selective. And then they can etch one kind of layer with a very high etch rate while not touching or having a very low etch rate on another layer, the resist, a protective layer, silicon, or whatever is underneath. So the dry etch can also be selective, can also be non-selective. We call it physical etch versus chemical etch. A chemical etch can be selective or non-selective depending on the layer it needs to etch. Physical etch is usually non-selective. Why? Because if you bombard something with argon, usually you can sputter it out. And it doesn't matter if it's silicon, if it's resist, you physically heat it and make it go away. So physical etch is not selective, or mostly not selective. Chemical etch can be selective or non-selective depending on the chemical you use for etching and the chemicals and the material you are etching. Okay, yes? Yes, but I will not go into it. This is not commonly used. What is the advantage of dry etch over wet etch? So, as you can see here, we can produce very straight etch. We can get to, we can avoid consumption of material beneath the protective layer or the resist. So this is one advantage. The other advantage is that since it's in one chamber, we can alternate the chemicals. So for example, if on top of this layer I might have residue of some other material, I start with a physical etch, very aggressive one. We call it breakthrough etch, that consumes almost everything. And then when I consume the top layer and I know the rest is clean, I can go into a more sensitive chemical etch. It could be selective. Now, the etch itself also allows me another thing. We call it endpoint. What is the endpoint? When the etch etches this material, it also produces light. Why does it produce light? This is a plasma process, and we excite the atoms. Once the atoms go to the non-excited level, they radiate. What do they radiate? Photons. Now, those photons, the wavelength depends on the material, on the energy level of the specific material. So, if, for example, we're etching here oxide, we will get radiation of oxygen and of silicon. And here, when we finished etching the oxygen, depending on the layer that is beneath, we will not get any more oxygen or photons related to oxygen. If it's silicon, we might get photon related to silicon, by the way, by a much greater amount. So we can get a signal by which we know, oh, you finished etching the oxide. Now you're etching into the silicon. So we get a signal that tells us when did the etch stop. We call it an endpoint. It tells us when we ended etching the layer we wanted. What do we do after we get to an endpoint? Do we stop? It's not good to stop. Why? Because maybe there's still some residue, maybe in the edges of the wafer, maybe some structures, the opening is big, so all the oxide was cleared very quickly. In some openings, the etch had a more difficult time to go in, and there's still some layer inside. So we usually do an overetch. Okay. So again, we get into control. We learn two ways to control. One is having a chemical etch, which is selective. The second is using an endpoint. And the third is, on top of these two, anyway, do an overetch, just to make sure you clean out the areas all around, or you compensate for tool-to-tool variation and so on. The endpoint also tells us, just a moment, the endpoint also tells us what was the real etch rate, assuming we know the thickness, or what was the thickness, the real thickness, assuming we know the etch rate. Yes? So dry etch potentially also affects the photoresist. or any other protective layer. For example, when we do physical etch, for sure it affects the photoresist. For a chemical etch, it depends which chemicals. Now, we try to choose the chemicals in such a way that they will not attack or will attack at a very low etch rate the protective layer, in this case the photoresist. No, chemical etch. In dry etch, we have two components. One is physical etch, when you bombard the layer with atoms, usually argon atoms, which are big. And by the way, they're not active chemically after they relax, because they get back all their electrons and they just move out. And the second way is to accelerate chemicals, for example, chlorine or hydrogen, that attack only specific materials. Okay? So chemical etch can also be done in dry etch. Okay. This is a true life example I worked on more than 10 years ago. And what we see here, this here is a nitride layer that was protecting this area. Here, there's another nitride layer. This area was not protected. And what you can see is the formation of the etch. Eventually, this structure will become an isolation structure between two transistors. This area here will serve as an area for one transistor. This will be the P-tip. And never mind the exact structure of this transistor. This will be what we call active area. Sometimes we call it diffusion area, that will be served for a transistor. Here, we'll do another transistor. This will be this can be an N-type transistor, and this can be a P-type transistor. So what is this for? This big hole? Isolation. Why do we need isolation? Why can't we put the N-type transistor very close to the P-type transistor? So they will short one to the other. And we will get some parasitic transistors that eventually will blow up the whole circuit. But if you get them too close, they will short. Now, then let's put them far away. What's the problem? Let's put them 10 microns apart. They will not short to each other. So why don't we do that? The space. So we can do that 10 microns apart, but then we lose 10 microns. So if we lose those 10 microns, eventually it translates to silicon area and cost. So what did we do? Actually, these transistors need about 1 micron to be apart from another in order to work properly. So what did we do? We etched a little more than half a micron here, a little more than half a micron here, a little less than half a micron here, and the transistors are now separated by more than a micron. But they're put very close together. Now, this is the etch we did, and eventually we will fill this by an insulator, I will show later, by a deposited oxide. This etch, I brought this example in order to tell you a bit about the etch itself. There are several layers, and although this looks very simple, it's not that simple. So here, first, we add resist. We do not see it on the picture because it was removed. So the first layer we had to etch was this layer, which was here, the nitride layer. So first, what etch do we use first? No. So first, we don't know exactly if the surface is clean. We use the breakthrough etch, a physical etch that obviously dry etch, which accelerate argon atoms, hits the surface and cleans it, and actually removes part of it. It removes depending on the time we allow, a very thin layer. The problem is that it also removes resist. So this would be the first step. What would be the second step? We would do some chemical etch. Chemical etch that consumes nitride. Now, ideally, what would be that etch? What? Dry etch, but what do we have below? We have silicon. So, what would be the ideal thing to etch the nitride? Selective. We want to have a selective etch for nitride in order not to etch the silicon at the first step. The problem with a very selective etch that it's also a bit slower. Why do we care? If it etches 2 minutes instead of 1 minute, what's the big difference? So if it etches 2 minutes instead of 1 minute, it means that we can produce from the same tool half the wafers. Okay? Now, we already paid for the tool. It consumes the floor area in the clean room. And instead of getting it a certain output, we will get half the output. It means that we need to build another clean room, buy another tool. Eventually, this is cost. So again, we need to optimize. So after the breakthrough etch, usually we do an etch which is pretty quick with a high etch rate. And then we stop it after some time, which is calculated in order not to finish this area. Okay? Now, after that, we go to a selective etch which consumes nitride, which does not consume silicon, which is the layer below. Okay, we saw, yes? Okay, so first we have a breakthrough etch. I'm not sure about the spelling. I'll fix it later. Breakthrough. Okay, then, okay, breakthrough etch. Physical etch, yes. Then after that, after the breakthrough etch, we do a fast etch of nitride. Okay? So the fast etch, we choose it to be fast. So the selectivity is not that good. Usually not that selective.
More selective than the break.
Yes. And then we have selective etch. After we do the selective nitride etch, what will we do? Also selective over etch. It can be the same kind of etch, the same chemicals. Okay. Now, we can do a selective etch. Another way to know when to stop the etch is the end point. So here we can use end point. Okay? The over etch is some extra time of etch to allow us to get rid of the layer we want to etch, even in some places where it stayed. For example, at the edges of the wafer, where it was the layer was a bit thicker, or you can use the same process as number 3, but you can use something else if you like. Usually, we do the same chemistry here and here. Yes, the difference is that you stop when you know you hit something, and then you continue for a certain time. Now, in yes, in the tool, it could be continuous. But for understanding the process, I divide it into different steps. Okay. So then we did a selective overage. We cleaned everything up to here. What do we do here? This is silicon. So we do a timed silicon etch. Why timed? Why don't we use selectivity, or why don't we use endpoint? Because this is silicon all the way down, and we don't know where to stop. So we have to stop by time. Now, after that, we have a few more steps to allow us to form this exact shape. Now, there are reasons for the shape. We want the bottom to be flat. Why does the bottom need to be flat? No. You're getting close. So what we do is, I said one is an N-type transistor, the other is a P-type transistor. So one sits in an N-well, and the other sits in a P-well. Now, the wells, one is here, and the other one is here. Now, sometimes there is an overlap between the N-well and the P-well. It's not always exact. Sometimes there is some underlap. We need to make sure that this overlap or underlap are at this area, because if we had a trench, this is called a trench, shaped this way, and the border between N-well and P-well cannot always be here. Sometimes there are some inaccuracies. We call it registration. And then the border is here. Then from the transistor, which is here, to the other well, say this is a P-well, this is an N-well, and in an N-well we have a P-channel transistor. So between here and here, we have a very small distance, not the original distance that was planned with this type of trench. So if this is flat, even if the border between N-well and P-well goes up to here, we still have all this distance to protect between the P-well and the transistor. The bottom point here, the bottom line is that the shape is very important. So I talked about this part of the shape. Why do we need this roundness, and especially the roundness here at the bottom? The answer is that this helps us better control the electric field and also the physical stress. So here at the corners, there's always more electric field and more physical stress. So we have a corner here of the silicon and a corner here. This one usually generates stress, and if we don't manage this correctly, it produces dislocations and problems. Sometimes I've seen dislocations that go up to the transistor level and then kills it. Okay, so this is just to show you there's a lot of thought behind every process step, and there are also a lot of empirical data to support the decisions. Should we take this etch? Should we take that etch? Another process step is implant. With implant, we create N-type or P-type areas. And here, for example, we took a blocking layer. It could be resist or a different blocking layer. And the implant goes only to the silicon in the area which are not protected. After we do implant, usually we need to do anneal. we need to heat the wafer in order to get the atoms we implanted, the dopants, into electrically active areas in the crystal. And you've learned all of that. Okay? For example, here we see, it's a bit difficult to see. We see the same isolation trench we saw before. You can see it here. Here it's flat, and here it goes up. This part is silicon. This part is filled by oxide, a deposited oxide. And here you can see the line, which is the silicon line here at the top. All of this is resist. And the resist is covering this part of silicon, but is not covering this part of silicon. Now, the reason is that this specific step is implanting the P-well. And we want the P-well to be only here. This would be an N-type transistor. And the N-well would be here, and this would be a P-type transistor. The resist is blocking the P-well implant from reaching the N-well area. Now, you can see that it's pretty much at the center, but as we understood earlier, even if this resist is not exactly at the center, because there's nothing as exact. There's always variation, and the most we can do is control it. So we control the variation of this resist, and it needs to be just on top of this flat area. There was a question. No? Okay. Here, yes. So you also implant into the oxide, but since the oxide is insulating, even if it has some dopants, it does not conduct anymore. It does change some properties of the oxide. For example, the etch rate of oxide which was implanted is higher, but it does not change significantly the electrical characteristic of the oxide. Specifically, the oxide is still an insulator, a very good one. Now, what we see here, the resist has some, we call this a foot. This thing, if not controlled properly, is very damaging to the implant. Think if the foot was this big up to here, then it would block some of the implant in these areas. And if the foot is not on top of an isolation, it's on top of active area, we get a different implant where the area of the foot was. Okay. Again, almost always we have a foot in the resist. The point is to control the variation and to make sure it's always the same. Okay. Diffusion. Diffusion in the sense of annealing. Annealing the implants. And how do we anneal the implants? We heat. We must heat. The analogy is think of a box of Lego. Now, the Legos are scattered in many ways. You want the Legos to be more tight together. So, what do? You shake it, right? You introduce energy into the system, and then the Legos find a place, and usually the level goes down. Another way that you can learn that from day-to-day activities is to take salt. You take salt and you pour it into, say, a glass, and then you want the level to go down. You knock the glass a few times. You put energy into the system. The salt crystals move a bit, and then the level reduces. You get the salt into a more stable energy level. That is exactly what we do with the crystal. After we implanted, the dopants made a big mess out of the crystal. Even the silicon atoms are not in the place they need to be. We heat it, we introduce energy, and everything finds its place, which is at a lower energy level. and then the dopants also become active. What is one of the artifacts, the side effects of annealing, of heat? We're improving the crystal, but we're getting diffusion. What happens is that we start with something like this, and it diffuses, and it goes to some other area. Okay, we can calculate it, we can control it. What's the problem with the diffusion? Overlaps is one issue, but more in general, the diffusion spreads the area, right? It consumes area. Again, we can take that area into account. We actually do that. And the next transistor or resistor or whatever will be moved, will be separated. But we consumed area. Okay? Consumption of area, as we said, money, that's bad. So that diffusion diffuses everywhere. Diffusion moves from the high concentration area to the low concentration area. So if you implanted at a certain point, say here, you will get diffusion to the side, to the bottom, and actually to all directions. So we try to minimize diffusion. What is the way to minimize diffusion? What controls the diffusion distance? Temperature is number one, and number two, time. So sometimes we need to have high temperature, but we try to do it at a very short time. We call it a rapid thermal process or rapid thermal anneal, RTA or RTP. And with that, we get very high temperature, but for a very short time, sometimes just a few seconds. And in that way, we can anneal the wafer with minimal diffusion. Another problem of diffusion is if this was a source and this was a drain of a transistor, and they diffuse, they get too close to each other. Worst case, they short. And even if they don't short, the channel length is not as well controlled as it was before. Because sometimes diffusion is a bit longer, sometimes it's a bit shorter. As we said, there's nothing exact. There are always variation. Yes?
Can't one maybe control diffusion with the high diffusion?
So there are ways to control diffusion with electric field. They're not practical in the semiconductor fabrication. Okay, yes? Yes, of course. That's why you don't see the resist here. Why can't you anneal with resist? What will happen to the resist? What is the resist made of? Mostly carbon atoms. So what happens to carbon when you heat it? It burns. Okay. So next is planar. Planar is the step where we can make the area flat. Why do we need to make the area flat? What? Start over doing what?
It's the contacts or
Yes, what do we need to do in order to do another layer? Yes, photoresist. Now, if we put photoresist and the layer is not flat, the focus of the mask will not be always at the right place, at the same place. And then it will produce variation, and it will not necessarily copy the mask as we wanted it onto the wafer. So if we make it flat, we can easily make the focus of all of the mask just on top of the wafer. If the wafer has some variation in topography, in height, some of the mask would be with focus, some of it would be out of focus. Okay? So If you do an error on a wafer, throw it away. Better to start over than to try to fix it. And so usually before we do lithography, we make sure that the surface is flat. Sometimes we cannot do that. Now there are some other ways to use planar in some integrated ways. I will touch them later. For example, for formation of contact, this is being used, and some other stuff. What is the problem with the planar? Think of it as a polishing process, because that's what it is. It has two components. First, we can put abrasive material, which say very hard material, which just makes tiny scratches and removes material. Can remind you of physical etch. So this is a physical process. And this will probably polish almost any material, depending on which abrasive material we use. If we use alumina or diamond dust, it will remove everything. Now, what happens if we introduce, instead of just an abrasive material, we introduce a chemical? What will happen? It can be selective. And what will happen is that we will polish some material at a high polish rate and some other material at a very low polish rate. This is the same idea, the same selectivity that we had with etch. Okay? It's a chemical selectivity, and we call this CMP. CMP, chemical mechanical polishing. Okay? So this allows us to be selective. Now, a planar also allows us another thing. We can have an endpoint. There are two ways to find endpoint with the planar. Once you get into polishing a different material, the friction is different. So the power the motor needs to turn at the same speed is different, and you can detect that. So that's one way to get an endpoint. Another way, in the reflectivity of the wafer changes when you get to a different material, and that reflectivity can be measured online while polishing. And this tells you you finished one layer and you reached a different layer. And I will not repeat it, but in the same way we do etch, selective etch and over etch, we can do polish, selective polish, and over polish. Okay? So just before the break, I want to say we learned all the words, all the different elements, and now we're going to write a story. Now we're going to put them at a certain order, and we're going to write a story. You can write many stories depending on the words you use and on the order you put them in. Okay? We are back, and now we will write a story with the words we learn. So let's start with the silicon. Silicon is the start material. It's in a form of a wafer, a round wafer, which I showed you earlier. And the first thing we'll do, we need an oxide. What will this oxide be used for? In a transistor, what do we need an oxide for? The insulator, which is the MOS capacitor or the gate oxide. Okay, so the first thing we'll do is grow an oxide. Now, how will we grow the oxide? Will we do it in CVD, in PVD, in diffusion, oxidation? So I heard oxidation and I heard CVD. You say PVD. Okay. So the answer is oxidation. The reason is that oxidation is the cleanest way of making the oxide. As I mentioned earlier, the interface is getting buried inside the oxide. Now, in certain processes, we do a sacrificial oxide. We grow an oxide, we etch it, and only then we grow another oxide, which will serve as the gate oxide. And the first sacrificial oxide is used just to clean the interface. Even with one oxide, since the oxide grows both up and into the silicon, the interface stays in the middle and it's trapped. Why is it important not to have in the interface any contamination?
Changes the threshold voltage.
Exactly. In a MOS capacitor, in a MOS transistor, those contaminations are surface charge, and they change the VT, the threshold voltage. Now, not only that, but sometimes they become traps. So they can discharge and charge and change the VT at different voltages differently, or at different frequencies, differently. So we don't want that. That's the reason we grow the oxide. Now, I failed to mention initially, but there are two ways of growing an oxide. Which are they? Dry and wet. Okay. What oxide will we grow? So depending on the oxide we want to grow. If we want to grow a thin oxide, we want to control it well, and we want a very low growth rate. So what oxide will that be? Dry. If we want to make a thick oxide, maybe it's a transistor for high voltages, then we will start with wet oxidation, and then eventually we finish with dry oxidation. Why do we finish with dry oxidation? That's one reason, but it also, since the oxidation rate is lower, it allows us to better control the thickness. But the main thing is, if we want a thin oxide, dry oxidation, thick oxide, wet oxidation. It helps us better control the oxide, the thickness, actually also the conditions. There are several other reasons. Okay, so this is the first step. Next steps. Did you see that? I'll do it again. Ready? Look at the screen. Okay. We deposit what will eventually be the gate. This is done in a diffusion furnace, but it is a CVD process. Why is this a CVD process? Why isn't this a PVD process? Why isn't this a oxidation process? Why can't it be an oxidation process? Because it's not an oxide, okay? Why can't it be a PVD process? So PVD is usually used for conductors. Poly is a semiconductor, but there are other reasons. We want the poly to be of high quality. Sometimes the poly also serves as conduction lines. So we want it to be high quality. In order to do that, it needs to be crystalline. It needs to be deposited at a high temperature. If it's not crystalline, the mobility is very poor. Okay. Can we do this layer as a single crystal layer? Can we deposit it as a single crystal layer? Because a single crystal has much better mobility than many crystals together. We call it poly, and the reason is that below the poly there is an oxide. If we want to grow it, and we want this to be a single crystal, we need to make sure that each atom falls in the right place. So the substrate needs to be a a crystalline substrate. Okay, think of taking eggs and putting them one on top of the other. So there's an egg carton, you put the eggs, and then on top of every few eggs you can put another egg. You can make layers and layers of eggs. But you need the basis, an egg carton, to be there. If you try to assemble in different places layers of eggs, and then when they get together, they're not matched. One is in one direction, another is in another direction. Okay, so they're not the same crystal. That's exactly what we get here. Polycrystalline, poly from Greek, many. Many different crystals of silicon, each and every one in a different crystallographic direction. Okay, so that is a polysilicon. Then we spin resist. The resist is poured, the wafer is rotating, and then due to the centrifugal forces, the resist is spread, and it's at a uniform thickness on the wafer. Okay, so we spun resist on top of the wafer, and that's the color we will use for the resist. Please remind me later to ask what is the right thickness for the resist. Okay? And later we'll also ask what is the right thickness for the polygate. What is the next step after spinning the resist?
Exposure.
Okay, we need to expose it to allow. Here is expose and then develop. First we need to expose it. And everything which was exposed to light changes the chemical. It changes the resist chemically, and it makes it either dissolve or not dissolve, depending if the resist is positive or negative. In this case, it's positive, so whatever got the light gets dissolved. And we're left with a line of resist. Now, take into account that what we see here is a cross-section, okay, a cut of the wafer. And this line continues into the board and also into this direction. Okay, we're just cutting it. Okay, after lithography, what do we do? So in this case, we want to do etch. There are several etches in the process, so when we etch poly, we call it poly etch. What etch will we use? So first we'll do a breakthrough etch, right, just to make sure there's no contaminants on the surface. And then there are several chemical combinations which are very, very selective. They etch poly, but they don't etch oxide or resist. And the selectivity is very good. It's about 1,000 to 1. So the etch rate of poly is 1,000 times greater than the etch rate of oxide for these chemicals. So we did etch. Which etch did we use? Dry etch. How can you say that? How can you tell that? Because the line is straight. We copied exactly the image of the resist. Okay, there are no missing parts in the poly here, which are called undercut. Okay. Yes, so we usually use dry etch. This is also very important to controlling the width of the poly. Why is it so important to control the width, the direction from here to here? This eventually will be the channel length of the transistor, which we want to control very well, because this eventually determines two critical elements of every chip. First is the speed, and second is the leakage. Okay. I will show some example for wet etch, but most of the advanced processes are dry etch. Okay, now we finished etching. By the way, so we did, let me go back. We mentioned that we did breakthrough etch and then a very selective poly etch. What do we do next when we finish with the selective poly etch? By the way, how do we know when to finish? So we know pretty much what is the etch rate and what is the thickness. So we know approximately the time. So we can finish by time, or we can get an endpoint. Because when we finish etching the poly, there are no more signals that in the plasma there's any poly. There's any silicon atoms. The etch rate is the etch is very selective, so we will not etch the oxide, and we will see a signal in the gas that the concentration of silicon atoms, which are the residue of the etch, is almost gone completely. So either through endpoint or just timed etch, because we know what is the thickness. And then how do we make sure that there are no more residue of poly in other places in the wafer or in other features which are not nice and open like this one? We do over etch. Now, how long will be the over etch? Let's start with which chemical will we use for the over etch? Will it be probably selective, the same one? And we can do it, since it's very selective, for a long time. Sometimes we do even 100% over etch. If we have a selective chemical, then we can say we etch 2 minutes, we do another 2 minutes over etch, because it's so selective. If it were not so selective, then probably just a few more seconds. So if we can do with a few more seconds, why do we over etch significantly more? To be sure, we remove everything, everywhere, in every thickness of poly, in every wafer, in every area in the wafer, in every area in the die, also areas where the etch has a very narrow area to go through. Okay. So the best way is if you get a selective etch. Then you don't worry and you can do 100% over etch. Yes. It's true, you lose time. Mm-hmm. Sometimes it's worth paying, sometimes it's not. Right now it is a bit difficult for me to explain the balance. So the best way is if you have an endpoint, and then anyway you need to do an over etch. Okay. So now we want to remove the resist. How do we remove resist? So we can illuminate it again and dissolve it again, but after going through etch, then it's not that easy to dissolve. So acetone, which is actually chemical etch, right? Which is a wet etch. So one way to remove it is by wet etch. Acetone is used in labs, in universities. We have similar chemicals used in the industry. And another way to remove resist, burn it. So we don't actually burn it, we call it ashing it, but the effect is burning. We introduce oxygen and we introduce heat, and we oxidize the resist, burning it, and then removing it. So what do we do in the industry? So we do both. Okay, just to make sure it's completely removed. Okay, and ashing it removes in certain mechanisms, and a wet etch removed in other mechanisms. Yes?
Introducing oxygen to bear silicon, won't it make the seeds? Won't it grow the silicon?
So in principle, yes, but now we need to think about the temperatures. When we grew this oxide, it was around 1,000 degrees. The ashing is done at around 400 degrees. So yes, it grows a little more oxide, but it's not significant. Okay. And by the way, those are exactly the kind of questions which one should ask himself when putting the story together, when doing the writing. Because if you do it wrong, then you grow oxide when you didn't grow, or you have a thermal cycle after you did the implants and the implants are moving, and many other problems. Okay. So one of the ways we use wet etch is to remove resist. So we remove the resist. Next, we want to do an implant. Now, one way to do the implant is to define with litho where we want to implant and where we don't want to implant. Now, here, we're going to do an integrated step, which is called a self-aligned implant. So let's see what is self-aligned to what, but then you forgot to remind me what was the thickness of the resist. How did we choose the thickness of the resist? Yes, the answer is enough to survive the etch. So in this case, it's poly etch. The resist can be very thin because the etch is very selective. Why do we prefer thin resist rather than thick resist? So depth of focus, and it's much easier to define a thin layer than define a thick layer. Think of the photons going in, the waves going in. If the resist is thick, the illumination uniformity changes with the depth. It's much more difficult to control where the light stops because it's very deep and the light gets a bit to the sides. So the control of what we call critical dimension, the size of the resist on the top is very difficult to control. If the resist is very narrow, the distribution of the light inside it is very small, and it's very easy, not very easy, but easier to control the size of it, the critical dimension. Okay. So we removed it, and now we're doing implant. Now, check and see. We implanted. I will show this again in a moment, but we implanted without a mask. This is not done frequently in processes. The reason here we could implant without a mask is that we're doing just one transistor and it's one type. So we could do many transistors of the same type. But if we add both, this is an N-type transistor. If we wanted to do P-type transistors in another area, we had to protect them with resist, with photolithography. Okay, so we didn't use resist. And still, we defined the source and we defined the drain. And this was done. This is the source and this is the drain. This was done, and I will show it again. This was done because the poly layer was actually also serving as the stop layer to the implant. And the implant that hit the poly layer did not get here, the area which will eventually be the channel. And this leads me to the next question. How did we choose the thickness of the poly? It needs to be at least the depth the dopant will penetrate. Okay, at least it should be more than that. Now, what would happen if it would be too thin? The dopants will penetrate. So depending on the amount, either they will shorten this, or even if they do not shorten it, if even a small amount penetrates, the VT, the threshold voltage changes. And that's something we don't want, especially since it's not controlled well, because it depends on the thickness of the poly, which might change. Okay, so the poly thickness is slightly thicker, and you can see here that the drain ends at the exact point the gate begins. And the same for the source side. Okay? So we call this self-aligned. We aligned the source and drain with the gate, and the alignment is done without lithography. So the alignment is perfect each and every time for every transistor. It's much better than if we had to align one litho layer to do the gate and another litho layer to do the source and the drain. We will always have either an overlap or an underlap. Now, for a transistor, we can't do an underlap because it's an open. We have to do an overlap. And then if we do an overlap, then the control of the channel length depends on the amount of overlap or underlap we did. So here, what would be the channel length in this case? So at least for now, it looks as it will be exactly the size of the poly. So if we defined it well at litho, we'll have a very controlled gate. But this is a very controlled channel length. But this is not exactly the case. We will see in a moment. What do we need to do next after implant? Why do we need to do annealing? We need to make sure that the dopants we implanted become electrically active. Okay? And another reason we need to do annealing, we will use it for diffusion. Can you see the gate here? The top of it is poly with an N-type doping, and the bottom is undoped. We want the bottom of the gate also to be doped. So what we do next is we do a diffusion and annealing at the same time. We put this in a hot furnace, several hundreds of degrees, say around 800, and we put it there for several tens of minutes. Another way to do it is to do it rapidly with just a burst of light. In advanced processes, we don't put it into diffusion for a long time, because what will happen, look, sorry, let's so can you see what's happening here? This is the way we implanted it, and look carefully what's happening next. Can you see? It all diffused. It diffused through the heat. Now, the actual case, it diffuses not only to the bottom, but also to the sides. So the channel length still has some uncertainty, some variation that depends on the diffusion. Okay? Any questions about the diffusion? We want to minimize the diffusion as much as possible. Sometimes, what? It can also diffuse to the oxide, but it's minimal. We want to reduce the diffusion to as much as possible, but some of the diffusion also happens later. How can the diffusion happen later too? What can be the cause? The gradient of concentrations exist even now, but it's not diffusing. What's missing? Heat, temperature. So if later we will have processes which have heat, which are hot, and for extensive length of time, what will happen is that we'll have unwanted or unplanned diffusion, which will hurt us. Okay. So we did the diffusion, and then, you're not looking, I'll do that again. Please look at the screen. After that, we want to grow an oxide. And this oxide can be grown or can be deposited. If the oxide is grown, then here it grows much quicker than here. Why will it grow quicker here? Because it grows on bare silicon. So the oxidation rate is much faster. And here it will grow much more slowly. Now, the choice of will we choose oxidation or will we choose CVD depends on many, many things. Let's mention one of them. How can we say if CVD is better or oxidation is better? Give me one way to choose between the two. Temperature, yes. What is the temperature of CVD? Pretty low, a few hundred degrees, maybe 400 degrees. Okay. The temperature of oxidation is typically around 1,000 degrees. So if we do oxidation, what will happen? We'll get diffusion. Okay, so sometimes we will prefer oxidation because it's a better quality. But in most advanced processes at this stage, we don't do oxidation anymore. Exactly for the reason you said, we don't want extra temperature. We want less thermal, we call it thermal budget. So less temperature times time to avoid unnecessary and unneeded diffusion. Okay. Yes. What? It depends on what we want to do. So I say in most advanced processes, we don't do oxidation, we do deposition. In some, we still do oxidation. For example, where the interface of this poly is very important. For example, in a disk on key, there is a flash drive. The flash drive contains the memory in what we call a floating polygate. And if this is a floating polygate, we need to make sure that no charge leaks outside or the memory is erased. So we protect it with oxide. But if that oxide is not of a very high quality, then we get leakage. So in this case, although the process is an advanced process, we do oxidation. Okay, so there are several aspects, and depending on what you want to do, what story you want to write, you choose the right words. Yes?
Can you introduce oxygen during the annealing to oxidize?
You can do that, and this is one way we do it in advanced processes. You do very rapid oxidation. So you introduce oxygen and you do a pulse of light. It hits the surface immediately to around 1,000 degrees, but just the surface, and then it cools immediately. So in a few seconds, you can grow a very nice layer of oxide. Okay. Any more questions about oxidation, this oxidation? Now, in this oxidation, what we do is we protect the gate. We make sure that the gate is isolated and insulated from what? Later, we will put contacts to the gate and contact to the source and the drain. Now, if there will be no electrical barrier here, then if a current could flow from the gate into the contact that will go to the source. Okay. Next, so now I want to show you an example. You can see The date is 1999. It's 11 years old. At the time, this was the most advanced process. It's an Intel process. And what you can see here is, this is the gate itself, the polygate. Just here, you can see a line with a different color. And here too, this was the oxidation I was talking about. In this specific process, we did another oxidation, or rather, it wasn't oxide, but it was nitride. And those are these two big things here. This one and this one. So you can think of it as a second oxidation, or as a second buffer. We call it a spacer. Why? Because it spaces out the source and drain from the gate. You see? This is the amount by which we space this out. Now, what you can see here on top is called the salicide. It's a chemically activated metal with silicon. So the metal and the silicon combine, and we get what is called, the compound is called a salicide. So in the industry, we use aluminum salicide, cobalt salicide, nickel salicide. And the reason this is put here is to allow much better conductivity of the poly line, because the poly doesn't serve only as a gate. It also serves as a line to connect between things. And sometimes, we will see in the next lesson, this line is connecting one transistor gate with another transistor gate, and it serves as two gates. So it needs to be conductive. And this is the salicide. We can see here this black thing, and this is also salicide. You can see it's not well controlled. And the channel length is about here. Here we do not see it, but there are implants, and also here there are implants. Okay. Now you can see the size here is 90 nanometer, which is about the size here on the top. Okay, 90 nanometer is about 1/1000th the thickness of a human hair. Okay, a human hair is about 90 micron, and this is 90 nanometers. Okay, here a different kind of transistor, a bit older than the previous one. You can actually see here a very thin white line. This is the gate oxide. Okay, you can see here and here the oxide we just deposited, and also here there are nitride spacer. Now tell me, what happened to the oxide here? Exactly, there was wet etch. We had to clean something else in the process, which is not shown here. We put it in a wet bath, in a chemical bath, with chemicals that, what can you say about their selectivity? Very high. What does it etch? Oxide. What does it doesn't etch? Nitride. And what else? And silicon. Okay. So this is an example of a transistor, a real case transistor. This picture is also from '99, but this transistor is a couple of years older than the previous one. Okay, so now we want to cover the transistor and deposit a dielectric layer, an insulating layer. We want this insulating layer because eventually above it we will put metal lines, and we don't want the metal lines to touch the silicon. So how can this be done? let's assume it's an oxide. How do we make it? Should we do it in PVD, CVD, or oxidation? Why don't we do oxidation? Temperature is one reason, and another reason? The size. This is huge. If we have to get an oxide this big, on top of the silicon, it will also be about the same size inside the silicon. It will consume all of the transistor we just made. So we cannot do oxidation. So we can do, usually for oxide we use CVD. It depends on the process if we want to do a high temperature CVD or low temperature plasma CVD. And again, you already know the reasons why to choose one or the other. Okay, so we deposited this film with the CVD, probably plasma CVD for the lower temperature. What do we do? What happened here, by the way? Why is this higher than this? Because of the gate. When we deposit, then we deposit, say, 1,000 angstroms here, and also 1,000 angstroms here, and also here. So the thickness we deposit is the same everywhere. So I did not talk about how to make a spacer, but if you have a spacer, it's just like extending the poly a bit more. So we also have this bump. Okay, so is this helping us or disturbing us? Yeah, you already got to the solution. But what is the problem? What does it disturb? Later, we're going to do lithography. So it might distract, it might disturb the focus. So we will polish it first. So, okay, we just polished it. Went away. Okay, how do we know where to stop? How to stop? So, you can see that we finished, and it's a smooth surface. There's no way to know if we polished this amount or if we polished deeper. So we cannot use any endpoint. We need to use a timed polish. There's no other way in this case. So the friction also didn't change much because it's the same material.
But the amount of material you are scratching is different.
Yes, you're right, but it is not different enough. I did not teach about polish, but the pad also conforms around. Anyway, the signal in this case is not strong enough that you can use for endpoint. Okay? What will we do next? Yeah, so we did the source, drain, and poly. From an electrical point of view, what do we need to do next? Contacts. Okay, so in order to do contacts, we need to do lithography. Okay? We move to... So we spin the resist. Did you all see that? Okay. 10 years ago, that was exciting. These days, it's not. So we deposited the resist. And by the way, I'm teaching this course almost 10 years now. And the animation at the time was state of the art. I updated some of the material, especially what I'm going to teach in the next lesson. Because in some cases, the words and the principles stay the same, but many cases, we have to update. This industry changes quite quickly. Think about all what you have now. We could not produce it 10 years ago. And we'll talk about why later. Yes, we spin the resist. You drop drops of resist on top of a wafer which is rotating and then the resist hits the wafer and gets spread very evenly. The thickness of the resist depends on the viscosity of the resist and on the speed of the wafer. Okay. So now we put the resist, and then we need to expose it, right? Where do we need to expose? How many places? Let's see. Okay, can you see? It's a bit more difficult to see. We expose it in 3 places: here, here, and here. Now, we did not expose it all the way. Why? Because we don't want to make a line. We just want to make a contact. So we exposed it only in this area. You see the exposure does not go back much, and by the way, doesn't go much to the other direction. It's a very small area. Okay. So what do we do after we exposed, we developed, and now what? Okay. So this is going to be tricky. Let's think about the edge. How should the edge look like? So first look at the screen. I will show you the edge. Okay? So we see an edge that goes all the way here and all the way here, but does not go anymore. So let's think about what kind of edge will we use. Number 1, what's the first step? We need to to etch this oxide. To etch this oxide. So what would be the first step? Breakthrough etch. We want to make sure there's nothing else on top of the oxide. And then we need to continue and etch the oxide. Now, this oxide, the purple oxide, is different than the green oxide. The green oxide is more dense. It's a higher quality oxide. But it is still oxide. So after we do that, how do we continue and etch? So we probably must have a selective etch. At least for the second half of the etch, etching this, it must be selective. Selective, an etch that etches oxide and doesn't etch what? And doesn't etch silicon. Because if we don't do a selective etch, here, once it reaches the polygate, it will continue and etch the poly while it is continuing and opening this contact here. Since the contacts are of different height, the etch must be selective. Okay? It's a bit more complicated than that, but this is the principle. Yes, of course it must be dry. Now, the real etch has many stages. I'm trying to simplify. So breakthrough, no, the resist, we're not etching the resist. The resist was developed. So the etch is one breakthrough etch. Then we do an oxide etch, which is selective. Sometimes that part is broken into more than one step. And then after we do this, we get to the silicon at the bottom. And what do we do? So do we have an endpoint? Yes, we can have an endpoint because this is a different material. And so we know when to stop. And then what do we do after the endpoint? Overetch to complete the cleaning and to clean it also in other areas. So we do an overetch. And then we have these very nice holes. What do we need to do with these holes? Fill them. They need to be contact. Fill them with what? Metals. So in order to fill them, first we need to remove the photoresist. How will we do that? Ashing and wet etch. Okay. For example, sulfuric acid removes resist very well and does not harm oxide. Okay, so it is wet etch and it's actually selective. It removes the resist, doesn't remove anything else. And also doesn't remove the poly. Okay, we ashed it and then we etched it. It's gone. Now we can fill it. So now we want to fill it. There is one difference between CVD and PVD, which we didn't talk about. What? No. PVD is very directional, right? We sputter from the top, say, metal atoms, and they go and hit the wafers. So if we want to fill something which is very narrow, it's going to be difficult in such a way. And anyway, it will not stick to the sides of the contact. In order to have something that will stick to the sides of the contact, we will use a CVD. In this case, we will do a CVD of tungsten. This is the preferred material for contact. It is not the best conductor. What is the best metal conductor we have? Gold. Why don't we use gold? Too expensive, and also it damages the silicon. What is the second best conductor? The second best metal conductor? Silver. Why don't we use silver? Expensive. Okay. The third one is copper. We could use copper. Usually copper is not used for the first contact because it diffuses very quickly into silicon. And also there's a problem to fill this with copper. But tungsten has a molecule that can be used for CVD. The tungsten comes with that molecule, sticks, diffuses well inside here, sticks to the sides and to the bottom very well. So that's why we use tungsten. We could also, because there is no really good and friendly molecule for aluminum CVD. Okay. By the way, we do the CVD of tungsten, but at what temperature? Do we want to do it at high temperature or at a low temperature? We will insist doing this CVD at a low temperature because we already have the source and drain here, and if we hit them, they will diffuse. Okay. So then we get what we call a metal plug. This was created by CVD, usually by CVD. Sometimes we do a combination of CVD and then another CVD, or CVD and PVD. There are many, many combinations. Just in order to keep this simple, I will say we did it in one step of CVD. Okay, what is all this material here above? We wanted just to fill the contacts. How did we get all of this here? The CVD goes everywhere. It covers everything. It doesn't go only where we want it to go. Okay? And actually that's the reason we wanted to use CVD, because it goes everywhere. It goes very well into the contacts. But we don't need all this. So what can we do? One way is to etch it, and actually in some cases we use the etch. Polishing. So now this is an example where we use polish, but not only in order to make this flat, but also to create some integrative element, in this case the contact. So we polish it, and the polish will be selective. It will polish very well tungsten, and it will not polish very well the oxide. It will polish the oxide at a slower rate. Okay? And also, we could get an endpoint from the polish depending on how sophisticated is the tool. So, when it's covered with tungsten, how does the wafer look like? Shiny, very reflective, yes. Now, after we polish, and only the contacts are filled with tungsten, and there are not a lot of contacts, it looks like glass, okay? Not like metal. So this is one way to find the endpoint. And after we find the endpoint, what do? Over polish. Okay. Next, we deposit a metal line. What will this material be made of? Or either aluminum or copper. In this case, aluminum. Copper is done usually in a different process. We don't deposit it. We first etch the place and then deposit the copper into the place. It's called the Damascene process. Damascene from Damascus. But we'll talk about it. What? It used to be the way that people would decorate swords and other things. So they would make a scratch into a sword, fill it with some material, and then polish it in a similar way that we did with making the contact. But that's the way we do copper. But now we will deposit a metal layer and etch it. And we don't etch copper doesn't etch very well. In order for a material to etch well, the byproduct of the etch needs to be volatile. It could get out of the chamber. It needs to be a gas compound. And with copper, it's very difficult. So in this way, what we do is aluminum. We deposit aluminum. What do we need to do next? What? Lithography. So I will not show the rest of the process because then we do lithography. You already know that. And then we do contacts between metal 1 and metal 2. Then we do metal 2 and then another set of contacts and on and on and on. So what we can see in these cross sections, you can see a transistor here and here. These transistors are of the same type. How can we know that? Well, first of all, because there's no isolation between them. And the second is you can see that they have a contact, the same contact to one drain and one source. So they're actually connected together. So this is a transistor. Here we can see a contact. Here we can see the first metal line. Now you can see that the metal line stops here, and then there's another metal line here. You can see that this place and this place are connected through the metal line here. Okay? You can see these two transistors have the same contact. They're connected through one's source and the other one's drain. This is the contact to probably the source of this transistor. Here, this is N-type transistors sitting in a P-well. This is a P-plus connection to the P-well. So we actually also control the body voltage of these two transistors. Okay, and this is isolation usually used to isolate between N-type and P-type transistors. Any questions about this?
What is the between the two P-type?
Yes.
There's another channel.
Isolation.
Yes.
We can do even without this, but this is a byproduct of the way we design and place the contacts. So every contact to the P channel has isolation around it, even if there's another contact next to it. It doesn't need to be there. Okay. Here we can see another transistor, a more advanced version. The previous ones were by Intel. This one is by IBM. We can see a transistor, and this is silicon on insulator, the blue layer, and all of this is an insulator. And you can see one contact to the source of it, another contact to the drain of it. Okay? Silicon on insulator, there's several reasons why to make it. You can control the body voltage separately for each transistor. And I won't go into circuits, but there are some other advantages as well. So these are the contacts, and here we can see a metal layer. By the way, the colors were made artificially. The picture was made with a scanning electron microscope, which just gives you different voltage levels that you can translate to different levels of gray. Okay? Here you can see another Intel process in this case. Can you see this little thing here? This is the transistor. Okay? These are the contacts. You can see they're much bigger than the transistor. This is the first metal layer. This was done with copper. This is the next contact, the second metal layer, another contact, another 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 metal layer. And actually today there are 9 and 10 layers in more advanced processes. Why do we need so many lines? You know, we can get from every place to every place with just 2 layers of metal. So why do we need 6 here or 9 or 10 today? Capacitance, maybe. What did you say? It's faster, that's true. It's faster, yes. But if you use more layers of metal, you can get to where you need much faster in a shorter way with less capacitance and better resistance. But the main reason is, can you see another transistor? No, there's no other transistor. And let's assume there was another transistor. Think about the size of these contacts and the size of these metals. So if we had to connect it to another transistor, the transistor had to be quite far away. A lot of the area is consumed by these layers. And we want the area to be consumed only by transistors, because transistors must have silicon. The metal lines can run, they don't need the silicon area. We want to use all the silicon area for the transistors. So if we have a lot of transistors very close to each other, it's going to be very difficult to connect them with 2 layers of metals. And the more layers we have, the more connections we can do. The lower layers are used to connect transistors which are pretty close to each other. And the high layers the very high layers are used to conduct VCC, VSS, clock, and big signals. Okay? What is faster? So if you want to get to a long distance, then this metal will be faster than this metal. Why? Because it has less resistance, yes, and also it's further away from other metals, so it has less capacitance. But if you wanted to use only these, then the transistor had to be very far apart one from the other. Okay.
Just one question. What's between the metal lines? What type of oxide? Silicon oxide?
Between the metal lines, it depends on what the process designer or the process integrator put there. So it should be an insulator, and usually if you can get an insulator which is insulating better, which has you get a smaller capacitance between the lines, it's better. So you want to have a material with low, we call it low K, low electrical permeability. Which material has the lowest K? Air, vacuum. And the number is 1. Okay, so what you can see here, it's all air. These are metal lines. This is metal 4, and then a contact. This is metal 3. You can see metal 3, contact, metal 2, contact, metal 1, and the transistors are at the bottom. But this was not made really with air. It was made with with oxide, and then we removed all the oxide just in order to make the picture. But that's not real. Some companies use air in some places, but it's if you do just air, what will happen? It will collapse. There's no support. Not these lines, but if you have long lines, they will collapse. Now, okay, so now we finished this lesson.